Welcome to my presentation about measuring PDN impedance using the Bode 500 and Picotest PDN probes. Basically you can do everything. Where I say Bode 500, you can also do the Bode 100. You just might get slightly different limits in terms of frequency or performance. In general, everything that I showed you also will work with the Bode 100. So my presentation will start with a short introduction about PDN impedance in general. What is it? And if you are not so familiar with it, why do we talk about PDN impedance? Then I will introduce the shunt-through, the two-port shunt-through measurement method as the measurement method of choice for low impedance values. We'll have a look at the difference between a two-port probe and a one-port probe. And then I will talk about the calibration and correction of the measurement. Then we're going to do a step-by-step procedure for how to correct such a measurement. And in the end, if there is time left, I'm going to demonstrate a live measurement that I have set up on the table here to you and show an example. Yeah, the PDN, the power distribution network, composes of many different parts. And it starts basically with the power source. Where does the power come from? Then the power is often filtered. So we have input filters. That's what we heard about already today. Then we have the voltage regulator module that brings down the voltage level to provide the right voltage level to the load. Sometimes there is a point load regulator at the load. And often there is also some output filtering. There are ferrite beads in designs, there are capacitors, decoupling capacitors that are used to filter the power, clean up from noise or to avoid interference from one load to another. In addition to these components, also the PCB lines, the boards, the planes, the wires, and of course the capacitors that are placed are part of the PDN network. When we are done with the PCB, then there is the package of the load, for example, where there is a lead, there are internal power planes, there is the bond wire, and there is on-die capacitance, and then we are like at the end where the load really sits. But the current needs to return to where it comes from, so the return path, of course, is also part of that consideration, and often it's a ground plane. So a very simple PDN model could look like this. We could have the voltage source, we could have some inductance and resistance that are representing or modeling the limited bandwidth of the voltage control loop. So the inductance gives a rising impedance with frequency, and that's also what you experience if you have a voltage control loop. The voltage loop cannot follow for infinite speed, so the output impedance rises with frequency. Then there is the output capacitor that takes over at higher frequencies. So that's the voltage regulator module, or a simple model of such a model. After the module, there is a trace that has some inductance and some resistance. Then there could be another capacitor, second output capacitor, and there could be a second piece of a trace, and then there could be a decoupling capacitor at the load, and then we have the load itself. In this case, drawn as a step load, because in all these PDN considerations, the goal is to provide a stable voltage to a varying load, and if the load steps frequently, that's of course challenging for the regulation and for the entire system. So if we look at that system, we see multiple LC components. We have like 3 inductors and 3 capacitors, so we can form resonant circuits. And some of these capacitors will have pretty low ESR values. For example, ceramic caps have quite low ESR values, and ferrites also normally have quite a low resistance. So if someone places a ferrite bead, the goal is not to lose power, so normally they have a low resistance also. And that means that the Q of these resonances that we see in this resonance tank can be quite high. So if we simulate the same system with some concrete numbers, like the voltage regulator module here, that's a buck with some small signal model behind, and then there is a trace, 100 nano henries and 10 milliohms, That's a quite long trace, a couple of centimeters. Then there is a 4.7 microfarad capacitor with 20 milliamps and 8 nanohenry parasitic inductance. Shorter trace with 10 nanohenries and 3 milliamps, and a 100 nanofarad second decoupling capacitor, because there is always a 100 nanofarad decoupling cap. There's 4 nanohenries inductance and 10 milliamps ESR. And then we have the load, and in that case, I use the load as the simulation or as the stimulus to measure the impedance at the V out point, so at the point of load here. And that's what the load sees. So that's the impedance profile at the point of load. At the low frequency, we have the output impedance or output resistance of the voltage regulator module that will depend on the loop gain, or on where is the sense line, or on the last resistance of the last trace, or of the traces of the resistance of the traces. Then normally in a frequency range of 10 kilohertz to 100 kilohertz, we have the control loop that acts, so the loop bandwidth is somewhere there, and this simulation contains different profiles for different compensators that all have a crossover frequency of roughly 50 kilohertz, but different phase margin values. So depending on the phase margin, you will see a different impedance profile at the frequency of the control loop bandwidth. Then there is a resonance of the 4.7 microfarad capacitor and the trace and the VRM. And then there is another resonant peak from the 100 nanofarad capacitor with the ESL and the trace and the ESL of the previous capacitor. Yeah, and if we look at 200 kilohertz, so this first peak here, that's at 200 kilohertz, then we get an impedance of roughly 300 milliamps. And that would mean that if we have 1 amp load step, the voltage would drop by 300 millivolts. And if you look at 3 megahertz here, then we have 3 ohms of impedance. And that's even worse, because that would mean that we would have a 3 volt drop in case we have a 1 amp load stepping with 3 megahertz, or with a fundamental content at 3 megahertz that is 1 amp. Then we would see a voltage drop of 3 volts in that frequency range, which of course is way too high, or could be way too high. So the goal is to avoid these supply impedance peaks, because they can violate the target impedance. The target impedance is there to specify a maximum impedance that allows you to ensure that the voltage ripple will not exceed what is allowed when the current load steps. Also, this high impedance increases the risk of coupling noise to the supply voltage. If you assume a constant power noise source, then the voltage is the square root over power times resistance. So if resistance or impedance is higher, then the noise will be higher. This noise can then degrade the performance of parts of your circuits, like reference voltages and then ADCs or amplifiers and oscillators. It can cause jitter as well. And in worst case, these frequencies can even stack. And if you have dynamic load currents with multiple frequencies at the same time, or not even, it does not need to be at the same time, if they have the right order, then they can superimpose. And the worst case scenario means that 2 frequencies stack on top of each other and that you get a rogue wave. And there is the so-called flat impedance approach. That means avoiding all the resonant peaks, or avoiding the resonance peak that you can avoid. And that would mean that you avoid this possibility of stacking frequencies. So in this picture, you see a red curve with multiple resonance peaks. There is the first peak from the VRM, then there are 2 peaks from the decoupling network, and then there is the last peak that is from, or simulated from, the chip package that is formed by the on-die capacitance and the bond wire in the chip package. Normally we don't know where it is exactly, but if you follow the blue line that tries to avoid these resonant peaks, then you can see that even the impedance peak in the chip of this simulation reduces. So it's a way of not only avoiding the frequencies or the resonances in the decoupling network, but also lowering the impedance peak in the chip of the load. And that's a picture of such a rogue wave. Thanks to Steve Sandler from Picotest for capturing this or exciting this rogue wave. And here you can see two main frequency contents. You have this slow ripple from one frequency content of the load, and then you have this fast ripple from a second frequency content. And in that case, unfortunately, the high frequency content occurred at the peak of the low frequency ripple, and then the voltage stacks up, and the total ripple is nearly double or more than the single ripple would be. Yeah, so if we look at such a PDN impedance plot, it can, or why do we want to look at it? First of all, it can be a design goal in PDN design. If you talk about target impedance, of course, you need to ensure that the peaks are lower than the target impedance. Then it contains information about the stability or oscillation tendency of the voltage regulator. We have seen that in the simulation before, where different phase margins cause different profiles at the crossover frequency of the voltage loop. And you can immediately see if there are critical resonances, high Q resonances in the decoupling network that one might want to damp. So since there is so much information included, I suggest that we measure it. There is just a little challenge in that involved, and the problem is that generally the PDN impedance is pretty low. So we are talking milliohms, in high cases maybe hundreds of milliohms, and even below milliohms, it could be also in the micro range. And when measuring low impedance values, the measurement method of choice is the two-port shunt-through measurement. The method works by connecting the vector network analyzer, or our Bode 500, the output source to the device under test, and measuring the voltage drop using channel 2. So it's emulating a 4-wire Kelvin connection where 4 points of contact go to the device under test, and that's very important to remember. The setup provides high sensitivity for low impedance. That's good. It emulates a 4-wire Kelvin connection, so you can get rid of the contact resistance. That's important if you want to measure milliohms or even below. And it can even be used to measure in the micro range. When we talk about the 4-wire Kelvin connection, I said it emulates that connection. Why emulate? Because it does not really have 4 wires. If you think about it, in the Bode itself, the grounds are 1, or 1 as much as possible. There is 1 ground actually, or 1 ground, solid ground, the housing or front panel or the shield housing inside. And we bring them from 2 sides, we bring it to the device under test. So it's not really 4 wires, it's actually 3, because we have the 2 signal wires and then the 2 grounds, which are 1 in the device, and that causes a problem that we will talk about in a minute. Basically, this setup is a transmission gain measurement, so it's an S21 measurement, and the software then calculates the impedance that is connected between the signal line and ground using the expression impedance is half the characteristic impedance times S21 over -1 minus S21. Yeah, and then in real life, we somehow need to connect the analyzer to the device under test. And the device under test often is a PCB with populated components. You have small or bigger components and SMD pads. In optimum case, you might have some test connectors or test points where you can place probes or even cables. But if it looks like that, how do we connect it to that type N coaxial connector? And there is a solution for that, and that's the Picotest PDN probes. There are basically two types of Picotest probes. We have the P2104A1 port probe, and then there is the P2102A 2-port probe. What is the advantage of using such PDN probes, or why could you use them? They have a high bandwidth and a flat frequency response. They are available in different coaxial connector styles. You can have it with SMA connectors, PNC connectors, or type N connectors. They feature a PDN cable, a Picotest PDN cable that has an ultra-high shield attenuation and a very low shield resistance. It is flexible and thin, so it's easy to move it around. You can bend it easily. It's not it's not stiff at all. That's really nice when moving the probe. The P2102A, that's a 2-port probe that I also have mounted here. Comes with 4 probe heads for different SMD styles, or yeah, that's 0402, 0603, 0805, and 1206. And the 1-port probes are available in different pitch sizes. They range from 50 mils to 100 mils, and I think they're even customizable by Picotest. The probes are available in 1x attenuation or in higher attenuation options if you need to measure higher voltages. Everything below 3.3 volts can be measured with 1x attenuation, but you will add loading to the device under test because you're connecting 2 times a 50 ohm port to the device under test, and you can reduce that loading if you use attenuation in the probes, and you can even increase the possible measurement range in terms of voltage of the device under test. So if you have very low voltage systems, the 1x probe is fine to go. If you have higher voltages like 3.3, 5, or 12, then you should use a probe with included attenuation. Yeah, the 2 probe types, the 1-port probe and the 2-port probe, I tried to compare them a little bit here. So the 1-port probe has a disadvantage. If you want to make a 2-port chance-through measurement, you need 2 of them, so you need 2 probes. That's a disadvantage, but it comes with an advantage. The advantage is you can have a flexible positioning, so you could even probe the PCB from bottom and top, or from 2 sides, and with that probing mechanism you can get into a power plane. So I tried to depict that here on the right side in that picture, where I have the port 1 driving or exciting and the port 2 measuring, and then there are 2 wires that connect into the power planes. And if you have a similar, or if you also add test points and calibration points with the same wire structure on the same PCB close by, then you can calibrate the entire setup into the power planes, and you can measure the power planes inside. That could be useful if you want to compare simulation to your measurement, and if you want to know what is really going on inside the PCB. So that's an option that you only have when you use 2 1-port probes. The disadvantage is, besides that you need 2 probes, there is a disadvantage that handling is more difficult. So you cannot, or at least I'm not able to position 2 1-port probes at the same time and hold the PCB and then start the measurement. That's like, I'm missing at least 1 arm for that. So you need a probe holder or something like that. That's a little bit more effort. There is also something else that you can do. If you have 2 1-port probes, you can also measure transfer impedance. So you could say, I want to see the impedance between 2 points. What is the impedance between that? Not yet, I'm not yet so sure what you will do with that information, but at least it's possible if you have 2 1-port probes. Then there is the 2-port probe, and it's only 1 probe, so it's basically 2 1-port probes in one, and it has 4 pins that go to the device on the test. And the advantage of that probe is that you can use it by hand, so you can position it and measure. So it's a lot easier and intuitive to handle. The disadvantage is that it's less flexible because you cannot do the same things you can do with 2 1-port probes. Yeah, I've drawn an example here, or a picture of an example. You can see the 2-port probe with a probe holder, and it directly probes from above to the device under test. So that's a demo board of Picotest, 256 amp demo board, or the same board with 2 1-port probes, also in a probe holder. You can see the 2 1-port probes. One comes from top, the other one comes from bottom, and you can probe the pads if you have pads with through wires that go into the power planes. Note that these are Clampman probe holders. There is more information about PCB clamping available on the website of Clampman. Yeah, and now, until now, everything sounded great, and now the reality kicks in, and I would like to explain a little bit about the troubles that we face in the shunt-through setup, and the major issue is the ground loop error. The ground loop error comes from the fact that the grounds in the device are connected. So we have the signal source in the Bode that has a ground, and we have the channel 2, the receiver, in the input channel that also has a ground, and it's the same ground as much as it can be done in real life. So it's not totally similar, but very similar. So the signal comes from the 50 ohm source. The driving current flows through the device on the test, and then we assume that it returns only via the left-hand side here. But in reality, the current will split, and part of it will flow back where it came from, and the other part might decide to flow back on the second cable because we have a current divider here if we assume roughly similar shield resistances on both connections. And this current that returns to the ground of the receiver causes a voltage drop in the cable shield of the channel 2 connection, and then the voltage that we are measuring at channel 2 is the sum of the voltage of drop at the device under test, so that's what we want to measure, plus the voltage drop on the cable shield, and that's what we don't want to measure. So that's a systematic error that is called the ground loop error. This error depends, of course, on the size of the cable shield resistance. It depends on the ground contact resistance, and it depends on frequency, because this simple picture that we show here is valid for DC, but not valid for high frequency AC. The higher the frequencies get, the lower this is a problem, or the less this is a problem, because the current will want to return over the coaxial cable where it came from. It will not try to make that big loop from the one port, from the source port to the input channel port, because that forms a big loop, and that would create a lot of magnetic field that takes energy, and that the current doesn't want to do that, so it will try to return through the cable where it came from. And also the value of the device on the test plays a major role, because the lower the impedance of the device on the test, or the lower the impedance you want to measure, the more this becomes a problem. And the lower the frequency also. So there are some ways to reduce that ground loop error. One possibility is to use cables with a low shield resistance and connectors with low ground contact resistance. One example would be the PDN cables that have a triple shield, so pretty low shield resistance, and screw type connectors like SMA and N that have a pretty low and repeatable ground resistance when you screw them on. Another way to further reduce the ground loop error is using a common mode choke. That's like introducing an extra inductance into that loop so that the current doesn't want to flow around the loop, but likes to return at lower frequencies. These are easy to use. They also don't disturb the measurement much at high frequency, but a common mode choke does not work at DC. And at low frequencies, the common mode rejection of such a choke might not be sufficient, depending on what you want to do. A second way, or an alternative, is to use a differential amplifier like the J2113A from Picotest. That's an amplifier that works down to DC. The disadvantage is it has more impact at higher frequencies, and the common mode rejection is also limited. In addition, an active solution always introduces a little bit more noise than just a passive device. One additional thing that I want to mention here is that it's advantageous to use a booster amplifier if you have an external amplifier on the signal source of the VNA that reduces the loading of the signal source, and that can also reduce device internal crosstalk. So if the signal source of the analyzer doesn't need to drive all the power, that's also an advantage in such a measurement. So if you can use an external amplifier, it makes sense to use it. Now, how can you find such a ground loop? And I did an example measurement on the exact setup that you can see here. So it's Bode 500, P2102 two-port probe, and the ground loop isolator of Picotest. And depending on what ground loop isolation is used, a 5 milliohm resistor has a different result at low frequencies. So here you can see that above 1 kilohertz, everything looks pretty much the same, but below 1 kilohertz, things start to differ. And the least common mode reduction or least ground loop reduction comes from the Bode 500 with the probe without any extra effort. And you can see that below 1 kilohertz, the error starts to become significant. Then I introduced the J2102A, the common mode choke from Picotest, and that brings down the frequency to below 100 hertz. So the error is like, is small down to 100 hertz. And then it rises again. An alternative would be the PLCM, that's an OMICRON lab common mode choke, that brings down the error even further because it has just more common mode inductance. But it wiggles a little more at high frequencies above 10 megahertz. And then in orange, the semi-floating differential amplifier from Picotest to J2113A, and that works down to DC. So here I started the measurement at 1 hertz, and you cannot see where it stops working, or it will not stop working because it also works at DC. So that was the ground loop error, but there is more. There is calibration and correction. With calibration and correction, you can account for the phase shift and the attenuation of the cables, the common mode choke, the probe, and also slightly compensate the ground loop error. You cannot totally get rid of the ground loop error because the ground loop error depends on the contact resistance, and every time you contact, it will be slightly different, so you cannot correct it completely. Every time you move the probe from through to short to device under test, it will be a little bit different, so it's really tricky to correct it. In the Bode Analyzer Suite software, you have two options for calibration or correction. And for such a shunt-through measurement, there is the option of full range impedance calibration or user range impedance calibration. And we suggest that the full range calibration is preferred if the frequency range is unclear. So if you're not yet sure, will you measure from 100 Hz to 10 megahertz or from 10 Hz to 100 megahertz or whatever, then choose the full range calibration. The advantage is it goes over the full frequency range of the analyzer, so you can select where you want to look at, change the frequencies, and the calibration will still be valid. It uses interpolation between predefined frequency bands to calculate the correction values. The user range calibration, on the other hand, calibrates or measures the correction values only in the frequency range that you have currently set. And that means if you change the frequency range, it will be rejected. It's not valid anymore. So you need to recalibrate. But the advantage is it does not use any interpolation. Then there are two options for calibration. You can choose to make a through calibration only, or you can do open, short, and load calibration. The through calibration normalizes the underlying S21 measurement. As I said in the beginning, it's basically a transmission measurement from output over common mode choke, probe, device under test to the channel 2. So if you lift the probe and you put it on a through calibrator where ground and signal are connected, like you can show in the picture, you can see in the picture on the right hand side, then you can normalize that setup with all the cables and the probes and the common mode choke. The advantage is it's only one calibration measurement. It offers good signal to noise rejection or good signal during calibration because there is no big attenuation in the system. The disadvantage is that the correction point is far from the impedance you want to measure later on. Through means like infinite impedance between signal and ground, and later on in the measurement you want to measure milliohms, and that's like infinite and nearly zero, so the correction is far away from what you're measuring. As an alternative, you could also do open, short, and load correction that will directly normalize to the open, short, and load standard, so directly to impedance. The disadvantage is it requires 3 calibration setups. You need to measure all the 3, open, short, and load. The advantage is it also includes a short. So there is a calibration point close to what you want to measure. The disadvantage is it includes a short, and the perfect short cannot be constructed. So this advantage can quickly become a disadvantage if you want to measure very low impedance values. And the Bode analyzer suite does not yet account for the resistance of the short. So the 3 setups are depicted below: open, short, and load, always between signal and ground. So I choose to go with the through calibration because of the disadvantages of the open, short, load calibration. And to improve that a little bit further, there is a simple short correction that you can apply. And that works as follows. The first thing is to characterize or model the short, and that's what we call known short then. So you can measure the DC resistance of the short, for example, letting 1 amp flow through the short, and then measure the voltage using a multimeter. You get the DC resistance value. Then you can determine the short inductance either by a simulation or by making an uncalibrated measurement and estimating the inductive or measuring the inductive rise and calculate some inductance from that and say, okay, then the model of my short is resistance and inductance. So you measure the short, you store that as a memory trace, and then you use an expression. So here in gray, we have a memory trace that is the uncorrected short measurement, and I call it short. And then we enter an expression that is impedance of the measurement minus impedance of the measured short, and then we are at 0. But the reality is the short does not have 0. It has 250 microohms and 900 picohenry, and that's what this yellow part of the expression does. It adds 250 microohms and 900 picohenries. An example of that measurement method is shown here. So that's Bode 500 with 2-port probe and the J2102 common mode choke. So first step is measure the short DC resistance. So that's where I put the short or the probe on the short pad of this Picotest calibrator. And I let 1 amp through using a lab benchtop power supply and measured 0.25 millivolt DC voltage drop. So that means the short has a resistance, a DC resistance of 250 microohms. The second step was performing a through calibration on the calibration board to account for the phase delay and the attenuation of the cabling, the probe, and the common mode choke. After calibrating that measurement, the probe is positioned on the short pad, and then a first measurement is conducted. And here you can see the impedance of that shorting pad measured. At low frequency, there is some residual ground loop error because the common mode choke is not perfect at very low frequencies, as we have seen before already. So there is some ground loop error that still stays. Then at high frequency, there is the inductive region where mainly the length of that of the probe or the distance of the probe needles determines how much inductance is left. And then we have the resistive region where we see the 250 microohms. So if we look at that inductive region, as an example here, the cursor was positioned at 10 megahertz, then we can read 900 picohenry. So here it's 885 picohenries. So we can assume that the short inductance is 900 picohenries. And that would be a model of the short now. Saving that curve to memory and naming it short helps to enter the expression then, and as discussed before, the expression would be the corrected impedance equals measured impedance minus the measured short plus the model of the short. And in this simple case, the model of the short was 250 microns and 900 picohenries. Yeah, and then step 6, measure something you know. And in this case, I put the probe on a 5 milliohm resistor. And after that, measuring the device and the test. And when we look at the measurement result, here you can see the light blue curve. That's the known resistor. That was the S&D resistor with the same pad size, or with a fitting pad size for the probe. That's 5 milliohms, and you can see the reading is 5.006 milliamps at 1 kilohertz. And then the darker blue curve, that was the device under test. That also had an impedance of roughly 7.5 milliohms at 1 kilohertz. Yeah, so how is that short resistance composed? That depends a little bit on two factors. That depends once on the head, on the probe head, so on how far the contacts are spaced apart. Of course, the further they are spaced apart, the higher the resistance gets. And also it depends on the conductivity or the resistance of the short where you put it on. So in that case, I used Picotest P2100 cal board, and the typical values I found was that for the 0402 probe head, it's around 80 microns, for the 0603 around 170 microns, for the 0805 around 250 microns, and the 1206 around 280 microns. There is a little bit of variation in that. That comes from the positioning. That's every time a little bit different, of course. There are spring tips inside, and every time you position it's slightly different. The typical short inductance that I found also depends strongly on the probe head or on the spacing of the pins. It's between 230 to 1100 picohenries. And note that if you want to go into the single picohenry range, so if you want to determine tens of picohenries, then it gets slightly tricky, because you will need to position the probe exactly the same way every time you contact. So on that last graph, you can see that if you push the probe completely onto the PCB, which means like zero distance, or the needles, the spring tips are pushed in completely, and then if you lift them slightly, then you can see that the inductance rises, because of course the loop area gets bigger the further you lift the probe. So every time you should position the probe at exactly the same way whenever possible. And of course, the smaller the contact or the probe size and the needle spacing, so the 0402 gives lower resistance, lower inductance, and less variation of the inductance over distance of the springs. So if you need to measure very low values, the smaller probe head will give you better results. Yeah, unfortunately, I was a little bit late in preparing my work, so I could not confirm these values with Picotest, so it might change later on, but I'm pretty sure that it works. Yeah, there is also the challenge of going ultra low. So what if you want to go below 100 microns, let's say? Then you need to use a short with a very low resistance. What you can do is you can use a solid copper or a solid silver. I tried with 1 ounce of solid silver. That worked as well as a solid copper, and the solid copper is a lot cheaper. Also, make sure that you suppress the ground loop error as much as possible. There are some papers from Steve Sander and Van Dannen where they calculated how much ground loop error you're gonna have depending on the common mode rejection. And the lower you want to get in the microohm region, the more common mode rejection you need. Why? the better the short is, and the lower the ground loop error is, the less you need to subtract to get to the value that you want. So let's assume we want to measure the weight of that feather. Well, it's probably not a good idea to put that feather on an elephant and measure the weight of the total elephant with the feather, subtract the weight of the elephant to get to the feather. The error will be pretty big, as you can imagine. So it's better to keep the elephant small. So keep the short resistance small, keep the ground loop error small, then you have less correction to do. Also, use short cables whenever possible. The shorter the cables, the shorter the ground resistance. If you use cables, it's preferred to use cables with a low shield resistance, such as the Picotest PDN cables. And don't forget to measure something of a known similar value, and note that 1 ohm is not the same as 100 microns. And if you're designing a layout that you want to measure later on, think about adding calibration and reference elements to the prototype layout, like through wires and through pads, shorts, and things like that, or 50 ohm loads and known impedance, like a 100 micron resistor or a 300 micron resistor. That helps in validation later on. And if you need to go very low, finally, you might want to use connectors that have less contact resistance than a probe. So how low can you really get? And when I was talking to Steve about my presentation, he said, like, you maybe want to ask how low can you get and think of a limbo dancer and get the picture of a limbo dancer. So I asked the AI to make a limbo dancer that goes under electric power. It's not really related to the PC. I also tried it with PCBs, that didn't work out at all, but like that picture the AI came up with. The lower the impedance gets, the more difficult it gets. And the higher processing power gets, the lower the impedance needs to get. So if you have 100 ohm requirements, then the impedance needs to be below milliohms to keep the voltage drop small. The limit of the measurement is a little hard to tell. You can increase the dynamics of the measurement by using an external amplifier, then you can get lower. Also, something important to note is if you're having nonlinear control algorithms like constant on-time control, then the measurement might and will be noisy, no matter how much power you put in, because the control loop is nonlinear. So if you disturb it with more signal, it will react different to a small signal disturbance. You will also see that on a load step. Bigger load steps will cause a different reaction than smaller load steps. So there will be some noise that you will not be able to overcome if there is nonlinear control involved. The noise floor of the Bode 500 without external amplifier is roughly at 10 microns. So that's a measurement that shows the Bode 500 noise floor in a 1 kHz to 450 MHz measurement. The signal source drives the short with maximum power. That's the worst condition for the signal source. And the receiver bandwidth was set to 10 Hz, and channel 2 was terminated to show that no signal arrives, and that's the noise floor of the instrument. Of course, if you add external cabling and connections, everything gets worse normally. But here the noise floor is around 10 microns. So an example of such a lower impedance measurement is shown here on that 256 amp demo board, where two analog devices, step-down regulators, are driven in parallel, providing 250 amps. And on the right-hand side, you can see the output impedance at 253 microns at 1 kHz. Also a little bit noisy at low frequency, and that's from the nonlinear constant on-time control mode. So even if you increase power, that noise will not really go away. What if you need to measure PDN impedance above 3.3 volts DC? That's where the instrument can get damaged because the 50 ohm input and output must be protected. There are some possibilities. You can use the three-port measurement, like the Picotest 2111B current injector, or you could introduce DC blocks at the ports That will, of course, limit the lower frequency that you can measure. Or you could use the shunt-through measurement with series resistance and use through calibration to remove the influence of the resistors. And that's basically what you need to do when you use the Picotest PDN probes in a 2x, 3x, or 10x configuration. Yeah, a little bit of advertisement for something that you cannot yet buy, but hopefully sure will be able to buy. So what are the benefits of our Bode 500? Like the Bode 100, it's an FRA and VNA in one device. It provides high accuracy and even higher dynamic range than the Bode 100. It's easy to use. It's controlled with the Bode Analyzer Suite. It features a USB-C connection and an Ethernet connection. It can be powered from USB PD and from Ethernet. Also, it's portable and lightweight. It measures from millihertz to 450 megahertz. And it's silent, so it doesn't have a fan. The Bode Analyzer Suite, I'm going to show that in a live demo now. And that live demo is already built up here. So we have a demo board that features a 5-volt input, then an input filter section that we can damp or undamp or remove the damping of the input filter. Then there is a DC to DC converter, and there are two paths. We have a 3.3 volt path and a 1.8 volt path. And the 1.8 and 3.3 volt paths are very similar. They can be adjusted having a good compensator or a bad compensator, and a Faraday bead can be introduced, and then the load can be changed. That's how the PCB looks like. So that's a picture of the PCB that is here. And currently I have placed the 2-port probe on that 1.8 volt test pads here. Yeah, input filter section, some reverse polarity protection, a jumper that is not placed, an LED to show that it's working. And here we have the LC input filter and the damping capacitor and a switch to remove the damping capacitor or enable it. Then there is some overvoltage protection, because if the input filter oscillates, it can destroy our chip. The chip is a dual DC to DC converter, and let's look at only the 1.8 volt section. So here is the output inductor, the feedback divider with injection resistor for a loop measurement, output capacitor, then a Faraday bead, and a second output capacitor. And then on the compensator, there's the possibility to choose between a high phase margin and a low phase margin compensator. The load is not so critical in that case. It's just switchable load between 100 milliamps and 300 milliamps, and there is a transistor to make some load steps. And that's how the PDN impedance looks like, but I'm going to show you that in real life now. So here you can see the measurement running. So the probe is contacted and the measurement runs. Yeah, and before I did that measurement, I also checked the short to see how the short impedance looks like. So very similar to the measurements I have shown before. This is the short impedance, and you can see that the impedance of the short is much lower than the impedance of the device on the test. In that case, that is above 10 milliamps. So in this case, the expression to correct for the short does not really change much. So the result of that expression is pretty much the same as without the expression. So you go low here, you can see, okay, it's very similar. So in that case, the correction of the short does not help much. So I will just leave it away. If you go to very low impedance, then you will see a big change when you correct for the short. So let's look at the data. We are measuring from 100 Hertz to 200 megahertz in that case, and we see the first resonant peak here at 21 kilohertz, and then a second one here at 500 kilohertz. First one, that's from the control loop bandwidth, and the second one, yeah, that's not really a resonance, that's the second output capacitor, and that's the first output capacitor. So let's store that into memory, and now I will change to a compensator with low phase margin. by removing a jumper and placing the jumper again. So now the phase margin of the control loop has roughly the same crossover frequency, or exactly the same crossover frequency, but a lower phase margin that causes the first peak to rise. And now I'm gonna introduce the ferrite bead between first output capacitor and the second output capacitor. And what you can see is that the DC resistance gets higher because of the series resistance of the ferrite bead. And then there is a second beautiful output resonance here at 150 kilohertz that is formed from the second stage LC filter. Also, this peak is pretty much distorted. That comes from the power level of the injection. So if I reduce, let's say, like to 0 dBm here, measurement gets a little bit more noisy, but the second peak, the deformation of the second resonance is gone now. Yeah, on this graph, I've even removed the damping of the input filter that I forgot now. The input filter resonance is here at around 10 kilohertz. And in that case, you can even see the input filter resonance at the output impedance of the system. So control loop bandwidth, farad bead, and yeah, control loop bandwidth is around roughly 20 kilohertz. Farad bead was at roughly 120 kilohertz. And if we make load stepping that has 20 kilohertz and 120 kilohertz content included, and look at the voltage ripple. So on the top you see the load stepping pattern, and on the bottom you see the output voltage ripple. So first there is like 20 kilohertz load steps, and then there is a certain period or amount of 120 kilohertz repetition. And in that case, the system was set to 50 degrees of phase margin, so that's a good phase margin case, and the farad bead was not in the system, so there was no second resonance. And you can see that the voltage ripple is around 9 millivolts peak to peak. And when having the 15 degrees of phase margin, so reducing the phase margin of the control loop, then the system reacts worse to the 20 kilohertz load stepping. So in that case, up to 30 millivolts peak to peak ripple from that 20 kilohertz load stepping. So that's the first resonance peak that you have seen. And if you bring in both resonance peaks, like the 20 kilohertz and the 120 kilohertz, and then you excite them both at the same time, then you can see that these frequencies stack, and now we get a total ripple of nearly 60 millivolts peak to peak by exciting both resonances at the same time. Yeah, as a summary, the PDN impedance plots reveal information about control loop stability, about resonance frequencies in the PDN network, and it's a rather simple measurement. Output capacitors are nearly always accessible. The control loop does not need to be broken. You just need to access the output. You can choose to go for the flat impedance approach to guarantee optimum damping at all frequencies. And note that lower output impedance also results in less noise on the power array. If you want to read more about PDN impedance, I have collected some references for you. And with that, I thank you for your attention.